So next, I have the great pleasure to introduce a CSAIL alumnus and member whose contributions to computer science have set him apart as a thought leader in a very important field. Professor Ankur Moitra's groundbreaking work in the field of algorithms and machine learning has consistently pushed the boundaries and brought together theory and practice. His research is deeply rooted in theoretical underpinnings, and yet it has remarkable impact in practical applications. So he really shows us that it is possible to bridge the gap between theory and practice. So please join me in welcoming a pioneer in theoretical computer science, winner of the Martin Award for the best MIT master's thesis, winner of the George Sprouse Award for the best MIT PhD thesis, CSAIL alumnus and CSAIL member, Professor Ankur Moitra.
Thank you, everyone. I just want to check my slides. Okay, great. All right, so my name is Ankur Moitra. I'll be talking about reinforcement learning. Now, this talk will really be about the foundations of reinforcement learning. But before I talk about the foundations of RL, I want to start off with the foundations of supervised learning. So in fact, in 1984, in a landmark paper, Les Valin introduced what's called the PAC learning model. So PAC stands for probably approximately correct. In fact, in 2010, he won the Turing Award in large part for laying the foundations of computational learning theory. Now, I'm not going to give you the full definition of what it means for PAC learning, but the rough idea is enough for this talk. The idea is that we're given examples, labeled examples from some unknown distribution, and we'd like to find a hypothesis that fits our data well. Now, PAC learning is going to be our inspiration for what we want out of RL2. So let me dig a little bit deeper into it. The key assumption that makes supervised learning and PAC learning work is the idea that there's a simple hypothesis that does well. But what kind of hypotheses should we study? This is really an important question because it's where we set the direction for our field. What kinds of functions does it make sense to try to learn? In fact, if you dissect it, there are really two components to a theory of learning. One is the statistical side. We want classes of functions where we can learn them efficiently using just a few labeled examples. One, is it possible to learn these functions without just memorizing all of the values they take? And the good news is that we have a very well-developed statistical theory of when it's possible. We have things like the VC dimension, the fat-shattering dimension, that give us tight characterizations of what classes of functions can and cannot be learned through few examples. But the truth is that a theory of learning is somehow incomplete unless you also talk about the algorithmic side too. So it's not just that we want to, in principle, be possible to learn, but we also want that there are efficient algorithms for doing so. And the main point is that when we think about both of these sides together, both the statistical and algorithmic, oftentimes the algorithmic side places a lot of constraints on what types of hypotheses make sense to learn. If you think about it, well, the only way that we can have a theory that actually makes sense and explains, how learning takes place in natural systems is if we have an algorithmic theory too. And that's where we get nice geometric classes of hypotheses, things like half spaces and the perceptron algorithm, and a lot of generalizations therein. So what I want to do is I want to take this inspiration with us to RL, and I want to ask for more than what people traditionally ask for. So in RL, it's a dynamic setting where you have an agent who's learning by interacting with the environment. So at every time step, the agent chooses one of several actions. That affects the reward that the agent sees. But crucially, it also affects the underlying environment. It affects how it evolves. And there's one standard abstraction, which is usually the starting point for RL, which is called the Markov decision process. So I want to tell you a little bit about what that is, and then I want to critique it and tell you why we need more. So a Markov decision process, it has a lot of terms, but it's a very natural thing, because at the end of the day, it's like a driven Markov chain. You have a state space S, you have a distinguished starting state S naught. You have an action space that tells you what actions you can play at each state. You have a set of rewards that, based on what state you're in and what action you play, tell you how much you profit. And the crucial thing is that you have a set of transition probabilities too. These transition probabilities tell you how your action affects the underlying environment. If you're at state S and you take action A, how does the choice of that action affect what state you reach next? What's the probability distribution? And finally, you have a horizon H, which tells you for how long you play the game. Now, the natural notion of what it means to solve an MDP is to find a good strategy. In our case, a strategy is very simple. It's just a rule that tells me that if I'm in this state, I should play this action. That's called a policy, and we want to find a policy that maximizes the expected reward. So this is RL in a nutshell, right? But the truth is, when we think about exciting applications of RL, things that are in the news that are really amazing things that have happened in practice, well, these plain vanilla settings, which are called tabular MDPs, because you can write down a full description of the problem, they're insufficient. And it's very natural to think about why that is. You can think about things like strategic games, playing chess or Go. In principle, you could write them down as a tabular MDP, write down the full set of states, but you could never do that because there are just too many states. You could never even hope to visit all of those states. So we need different abstractions that allow us to concisely describe a game without having to literally write down every possible state. That leads to things like function approximation and other abstractions. In fact, there are other settings in RL where maybe the idea that you see the state is the thing you have to push back against. You can think about applications in healthcare where the state you care about is really the state of the patient, but all you have access to are the tests that you can run on them and what are the outcomes of those tests. It gives you a window into what's going on, but it's not the full picture. Now, my main point is that all of these things are very well studied, but only from the statistical standpoint. We have an understanding of how to augment the standard model of tabular MDPs so that they're richer models for the world around us, the problems we really want to solve, in terms of how we're still able to get bounds on the sample complexity, but what about the algorithmic side? So what does it mean to get good sample complexity bounds? It means that we have some strategy for how the agent should play, how they should choose actions to learn about the environment so that after a small number of sequences, they can converge to a good policy. But what about the agent? What exactly is that agent doing? It turns out that modern RL is built on computationally intractable oracles. These models that we hold near and dear that are abstractions about modern RL, they're all predicated on the idea that the agent is solving wildly hard optimization problems in order to choose their sequence of actions. These are things that are not merely NP hard. In fact, usually they're p-space hard. So something I've been thinking a lot about these days is, can we take the same spirit of what Les Valiant did and bring it to RL? Can we rethink the foundations of RL and think not just about the statistical side, but the algorithmic side too? We have the same type of dichotomy that it's really two pieces of the picture, right? We have the statistical side where we want to know what are the appropriate abstractions so that it's possible to learn good policies with few interactions with the environment. And we have a well-developed theory with thousands of papers. We have things like Bellman rank, block MDPs, bilinear MDPs, decision estimation coefficients. These are all working towards the most general possible setting where it's possible to statistically learn. But what about the algorithmic side? I claim that none of these models are sufficient that way because none of them enable end-to-end algorithmic guarantees. So maybe we have to start from square one. We have to think about what are the right abstractions where we can have our cake and eat it too. So let me tell you one vignette along these lines. That's all I have time for. Let's talk about this thing I alluded to before that also came up in Tomas's talk, which is we take a Markov decision process, but now we no longer directly see the hidden state. So what if instead, for each state, we get some conditional distribution on observations? That gives us a hint about what state we think we're in, but it doesn't tell us everything. What's possible in the context of POMDPs? See, the usual trouble in my neck of the woods is that I'm a theoretical computer scientist, and basically everything in machine learning is wildly intractable. So this is no surprise. In fact, let me tell you why it's wildly intractable. It turns out something that we took for granted in the case of MDPs goes completely out of the window. See, in the case of an MDP, I told you what it means to solve an MDP. It's to write down a rule of when I'm in this state, I play this action. And that's very easy. When you have an MDP, what it means to find an optimal policy is it doesn't matter what happened in the past. All it matters is where you currently are. That dictates what state, what action you should take. But in the context of POMDPs, it's not quite so simple because you don't really know where you are. You just have hints. So in fact, the optimal policy takes the full sequence of actions and observations. All of these give you some idea about what state you think you're in, and that full sequence gets mapped to a different action. There are different ways to do it, but at the end of the day, all of the ways of even writing down an optimal policy, forgetting how I would even find this policy to begin with, well, they need exponential space even to describe them, either exponential in the horizon or the state space. But one of the themes in theoretical computer science that I'm a huge fan of is the idea of beyond worst case analysis. The idea is to stare computational complexity in the face and not blink. Because maybe the types of problems that we cook up in these hard instances are not really representative of the real things we want to solve in practice. Maybe we need new starting points, new assumptions. It turns out that if you stare into the guts of these hard instances, they all have this curious feature. It's not just that you don't see the hidden state, you see nothing. That's really a blind MDP where you play it without seeing where you're moving at all. But if you push back on this assumption, you get a much more realistic and tractable model. The idea is, what if instead you leak some positive information about your hidden state? You don't see everything, but at least you get a hint about where you are. And it turns out that these types of assumptions can totally change the game from wildly intractable to algorithmically possible. So I'll tell you roughly the definition that we work with is something called gamma observability. What this means is that observations are discriminative. That if you have two different distributions on the hidden states, B and B prime, and they're very different from each other, that the observations you see should give you a hint about which of those two states you're in. You can make this precise in terms of definitions with a total variation distance. But roughly what this allows you to do is it allows you to get, instead of exponential time algorithms, you get quasi-poly time algorithms, so wildly better. I'll mention, like Tomas, that this has all been implemented and it's very practical, but IBM told me I can't talk about it, so just wait 20 years. But in any case, I only have time for one key idea, really, is that a lot of the works we've been doing are about building a dictionary between reinforcement learning and control theory. So it turns out that the key idea that makes this work from a beyond worst case analysis standpoint is to study something that's called the Bayes filter. So if you tell me the whole POMDP, then I can talk about, if you give me a sequence of actions and observations, what's my posterior on which state I think I'm in. The key thing that we show is that the Bayes filter is exponentially stable. So it forgets the past at an exponential rate. This is actually a discrete analog of something that's been known in continuous but more structured state systems since the 60s, which is called the exponential stability of the Kalman filter, but it's exactly what allows us to get around these worst case lower bounds. So really, this is just one vignette in a much broader research agenda. I'm a theoretical computer scientist. I try and study algorithms. And when it comes to machine learning, when all the problems around us are computationally hard, well, usually my way out of it is to try and understand beyond worst case analysis. We really need algorithms and modeling to speak hand in hand to understand what are the right abstractions to study to begin with. And I think RL is one place where we really need to rethink some of these foundations. In the last couple minutes, I want to transition to a different topic, which is I just want to talk about CSAIL after it is the CSAIL birthday. So I just want to say thanks for the amazing and supportive environment all the years. I've been here a really long time. If you don't believe me, this is what I looked like when I started back in 2007 as a beginning graduate student. And every day I'm excited to get to work. It's really amazing to feel so inspired by the work you see your colleagues and students doing. We have a full day of talks ahead of us to hear about some amazing highlights in CSAIL research, but really every day is like that. Every day there's a new way that CSAIL changes the world. But I also want to say that when I think about CSAIL, I don't just think about the research impact, I also think about the community. That's why we love what we do, is because we get to share it with each other. We push each other to ask bold questions, to share our passions, to learn and teach each other. And we have fun, weird fun as well. This is a picture that I think captures a little bit about what I find so exciting in CSAIL. So this was a theoretical computer science group event where we had a bunch of graduating students, so we decided what better way to throw a party and celebrate all the amazing work that they did than have a full day of talks. I guess that's how theorists have fun. You can see that I'm dressed in a hockey jersey. I think I know the reason. I believe it was faculty dressed like students and vice versa. You can see some of the students in the right-hand corner, they overshot. They dress better than we ever do. But in any case, what was so fun for me was that we planned a full day of talks. Everyone around here is very busy. And yet it was hard to get people to stop asking questions. They were so excited to hear about what everyone else was working on. I planned breaks for the event, and people used it just to talk about research and drum up some new collaborations. So somehow every day in CSAIL, it's like that. We're just excited to get to work, to learn and teach each other. And as someone who's been here for 16 of the 20 years, I can't wait for the next 20. So thank you very much, and happy to take questions during the breaks.